Hey everybody, welcome back to another video. In this video, we will be looking at a time series forecasting model referred to as ARIMA. ARIMA stands for Autoregressive Integrated Moving Averages Model. Now that's a mouthful, but I'll be taking you through each concept step by step. ARIMA is one of the many models that you can use for a time series forecasting problem. Now, essentially, what is a time series forecasting problem? Time series forecasting problem is a specific data science problem where, given a data set over a period of time, we try to predict a KPI value over the subsequent years or over the next few years. That is the essence of a time series forecasting problem. Now, depending on what kind of data set are we dealing with, we will be doing a thorough analysis of the data before deciding what kind of model is best suited for this particular data set. Now, in a sense, the model that we are looking at today, which is ARIMA, it is comprised of these three different, I would say, sub-concepts. The first sub-concept is autoregression, denoted by A and R. The second concept is integrated, which is denoted by I. And the third concept is the concept of moving averages, which is demonstrated by MA. Now, essentially, all of these three sub-concepts are very pertinent to time series. Now, let's go ahead and without further delay, look at each of these concepts because each of these actually individually are models that we use for time series analysis. Now, one of the common themes that you would see recurring almost in these time series analysis problems is the problem of regression. Because with moving averages and with autoregression, what we're essentially doing is we are performing regression over a variable. But rather than creating a relationship between a dependent variable and an independent variable, what we are essentially doing is we are trying to predict the value of a variable in the future from the value of that same variable in the present and in the past. So as you can see over here, what the autoregression model does is that it takes the past values of a certain variable. It calls the technical term for this is lags, and using those lags, it tries to predict what the value of that specific variable be at time t. So as you can see over here, the value of xt is a multilinear regression of its value at time t minus 1 all the way till t minus p. So from this particular equation, what we usually say is the order of AR or the AR value of the model is of the order p. So P happens to be one of the hyperparameters that we provide to this ARIMA model when we are trying to fit our data in this particular model. So as you know that one of the interesting concepts in data science and machine learning is hyperparameter tuning. What hyperparameter tuning is what are the specific values that we will give to our hyperparameter or to our set of hyperparameters so that we get the best value for our optimization function. From a neural networks and a connectionist standpoint, you can say that we use the gradient descent method to find out what will be my optimal values of weights and biases that will optimize my loss function to its best. In a similar way, in time series forecasting problem, specifically to the ARIMA model, what we try and do is we try and find the best set of values for P, D, and Q. Now, what we are seeing right now is P. I will be talking more about D and Q in the subsequent slides, but we have to pick the most optimal values of P, D, and Q so that our model can fit the data to the best of its abilities. So as you can see, the way we choose the best P value is through a visualization called the partial autocorrelation function. We take the data set and we plot the PSCF graph, and from that we can have an idea of how many values lie beyond the rectangular boundary that is shown over here, and we approximate the value of P according to the number of values that lie outside of this boundary. Now let's move to moving averages. Now, just like we talked about the prediction of a variable in the future from its past values or lags, similarly, what moving averages does is it also predicts the value of that variable at a certain time t. However, this time, rather than considering the lags directly, what it does is it considers the noise or the difference of the value from the mean, and it tries to average that over a period of time to calculate the value of the variable at time t. So as you can see from the equation, rather than taking the absolute value, what we are doing is we are taking what is colloquially referred to as the shocks or the differences of the predicted values from the actual values of the previous time intervals. Now, keep in mind, in one of the future videos that I'll do, I will discuss the concepts in neural networks, and I'll be talking about gradient descent. And there are numerous ways in which we can actually improve the convergence of the gradient descent function. One of the methods that we use is gradient descent with momentum. And the idea behind using momentum is exactly that. We are trying to cumulatively look at how the errors accrue over a period of time and factor that in while we are predicting a value into the future. That is the reason why we use something called as moving averages of a certain order, which in our ARIMA model, it is given by the value q or the variable q. Now, these two are predominantly the sub-concepts that are involved in the ARIMA model. Now, remember, apart from ARIMA, there also exists a model called ARMA, which is ARMA. And in ARMA, we only give P and Q. In ARIMA, there is an additional variable that we give to our model apart from P and Q, which is the differencing factor or the D factor. Now, what is the D factor? I'll come to that. But before I come to the D factor, just like we saw earlier, we use the PACF graph or the partial autocorrelation function graph to construe what will be the ideal value of P that I can give to my model to get the most optimal results. In a similar way, for the value of Q, we use the ACF plot or the autocorrelation plot to see what is going to be the best value of Q that I can give to my model so that it can give me the most optimal results. Now, with that being said, now let's go to the final parameter, which is the D parameter or the integrated factor in ARIMA model. So, as I mentioned to you earlier, that in the ARIMA model, we have three distinct parts. We have the autoregression, we have the moving averages, and we have the integrating factor. Now, one of the things that we need to keep in mind when we are using models like ARIMA is that there is an implicit assumption that ARIMA takes into account as it pertains to the distribution of the data that we are dealing with. One of the assumptions that ARIMA makes is that this data distribution is stationary and there is no seasonality involved in the data set. So a time series data set usually consists of seasonality and trends, and the ARIMA model assumes that these seasonality and trends are not present in the data set that we are analyzing. Instead, it assumes stationarity in the distribution of the data. Now, this is an assumption that the model makes. So therefore, we need to validate whether in our data set, this particular assumption fits or not. And to do that, we use something called as a Dickey-Fuller test. The Dickey-Fuller test is a statistical test where the null hypothesis is that our data is not stationary. And so if our null hypothesis is that the data is not stationary, the alternative hypothesis will be that the data in fact is stationary. And depending on the p-value that our Dickey-Fuller test returns, we can construe whether or not our data set is fit for our analysis with the ARIMA model or not. So with these things delineated properly, And now that you have an idea of what are the different facets that are involved in the ARIMA model, let us briefly recap the hyperparameters. So we have P, which is the autoregressive order. We have Q, which is the moving averages order. And we have the differencing order, which is D. Now remember one thing, if I get the value of P from our Dickey-Fuller test above 0.05, which means that we are not able to reject the null hypothesis, then we need to perform the process of differencing. And we need to do multi-order differencing to see at what order are we getting a data set which is fit for analysis, which means at what order are we able to remove seasonality and we are able to get a stationary data set. So with that being said, the procedure of ARIMA usually is that we figure out whether we have stationarity. That's number one. Number two, we apply differencing if we don't have stationarity and there is seasonality in the data set. Three, we have to find out what are the optimal values of P, D, and Q that we can give to our model. Usually ACF and PACF graphs help us construing that value. Then we train the ARIMA model and we evaluate the performance using some metrics like the root mean square error and the mean absolute error. And then finally, we do a forecasting over a period of time. So now that some of the fundamentals are out of the way, let's go ahead and let's dive into a real world example for me to show it to you what a project will look like. So here we have, I'm taking a very, very simple data set to show you how this usually works. And so let me first go ahead and put the data set here. There you go. Alrighty, so again, nothing very complicated, a very simple data set, just one column with discrete values. And let's see what we can summarize, synthesize, and understand from this hypothetical data set. First of all, we will import our requisite libraries. Then we are going to import the data set in our data frame and we will look at the series. Now, if I just look at this particular series over a period of time, just by looking at it, I can construe that there is a problem with stationarity. And in this particular form, my data does not meet the requisite criteria of stationarity. Therefore, in my opinion, there will be some amount of differencing that we need to do to come to that specific conclusion. But to make it much more concrete, let me go ahead and do the Dickey-Fuller test and get my p-value. So as you can see, my p-value is 0.12. Now, because it's a value that is greater than 0.05, we are not able to reject the null hypotheses. And therefore, we have to go ahead and perform some amount of differencing to make sure that we are getting to some temporary form of stationarity so that we can continue our analysis. Now, as you can see in the next part of the code, we have, so this is the original series. This is the first order differencing. This is the second order differencing. Now, let's see what are some of the p-values that we get from first order and second order differencing. So first order differencing, we got very, very close to actually rejecting the null hypotheses. But with second order differencing, we are absolutely certain that now we have removed seasonality from the data set. And with the second order differencing, we can go ahead and we can do our basic analysis. Now, with first order differencing, we get this particular partial autocorrelation plot. We can see that we can safely say that we can take a value of 2 or 3, because given the rectangular bounded box, I can clearly see 3 values that are over this particular bounded box. Let's keep printing. Now, this is the autocorrelation. This is the partial autocorrelation, and this is the autocorrelation. Now, remember what I told you about partial autocorrelation and autocorrelation. To predict the value of P, we go with the partial autocorrelation, and to get the value of Q, we go with the autocorrelation. So this, so as you can see that with PF for the PSCF, we took the value of 2, and with ACF, we took the value of 3. Now remember, these are not hard concrete values that we have to stick with. We can also perform auto ARIMA on the side, or we can run a loop where we are iterating over certain values of P and Q to see, okay, what is the best result that I can get. So when I kind of fit my ARIMA model over here, and let's see what results that we get. So this is how you things are going to look like when you will be fitting that particular model. So here, once we plotted 2, 1, and 3, uh, these are the coefficients that we are getting. These are some of the statistical analysis that we are getting. Uh, as you can see, we have the standard error, and we have the AR value and the MA values given. Uh, and therefore, also what we try and do sometimes is we try and see if we take different values, what kind of results that we get. So as you can see over here, this is the values that we're getting from 1, 1, and 1. As you can see, the p values over here, which is p greater than z, they have reduced themselves to 0. And let's see ahead. And once you plot the residuals, this is how we get we get the residual plot. And then finally, let's actually, once we have fit the model, let's go ahead and see how the fitted values look like in comparison to actual values. So it's quite good actually. The model that we end up fitting, it's really identifying the trend within the data set. So this is how you will do uh, you know a time series analysis. Sometimes we need to take different permutations and combinations of PD and Q just to make sure that we are actually getting the most out of our analysis. These will differ from one use case to the other, but I believe that through autocorrelation plots and through auto-ARIMA tests, we can reduce the number of possible values to a fixed set, and then we can go from there. So this is, sort of broad strokes overview of the ARIMA model in time series forecasting. Now, we did a real world project with this where we took a CSV data, we built a business logic, and we created interactive Streamlit dashboards to basically show you how the data is varying over the years, and how the trends are changing. So we have a sales data which has sales of products for specific years, and as you can see, this is very Power BI inspired. So even if you look at the color codes, it's black and yellow. uh, so this is how it varies over time. I have given specific filters so that you can play around with it and see uh, however and whatever products you want to visualize and you want to see. And depending on what filters you choose, this graph is going to change accordingly. Similarly, I have tried to apply ARIMA in for this particular uh, data set. And what we were getting is that I believe that in this particular data set, there was no synchronous patterns that were captured along the time series, which is why whenever I was trying to predict uh, the value in the future based on the data in the past, sparsity played a huge factor. And every time I was getting this kind of a linear straight line with which kind of represents that the past is very much determinant of the future, and there are no highs and lows and ebbs and flows that the data or the model is able to predict from the data set, essentially, which is why, because of the abysmal results that I was getting from ARIMA, I was trying to compare it with, a model like LSTM. And if I just go and if I type a custom value, and if go ahead and say 1 year to 1 historical to 2 years, uh, what it is showing and how it is showing. So as you can see that there is little trends with respect to the LSTM, but there is almost zero variation as it pertains to ARIMA. Carefully look at it, how much LSTM is sort of you know showing a little more trendy behavior as comparison to ARIMA, and the values have been captured over here. Although I would say that the variation is pretty negligible at this point with LSTM, but more or less there is at least some trends that I can see with LSTM that I'm not able to see with ARIMA. Therefore, it's imperative, ladies and gentlemen, to tell you that data science and machine learning is never a one size fits all approach. That always have to take a horses for courses strategy where every single problem needs to be dealt independently, and we need to pick specific models to deal with specific problems. Now, what I would want you to do is, if you want to uh, understand what was the process involved, what is the data set, and how did we perform the analysis, you can read my Medium blog to get a better understanding. And this particular dashboard is deployed in Streamlit. The link to the dashboard, the GitHub repository, and the blog will be in the description, so you can check that out. In the future, I'll be making specific videos on a lot more interesting models. And I was just reading this book by Pedro Dominguez called The Master Algorithm, and he has done a really good job when it comes to making people understand, even data scientists like me, but also to the average person, what are the kinds of algorithms that we are dealing with? What are the broader tribes in which they fall into? And this is sort of giving me an interesting framework of how I want to structure my videos in the future. So keep an eye out on that. And definitely, if you like this video and if you find some interesting insights from it, give me feedback. Like, tell me what do you like about this video? What do you want me to do more? And with that being said, I really appreciate your time. Thank you so much for watching, and I will catch all of you all in the next video. Thank you.